Alright, this is the method of joints. So this is a way to solve truss problems. So if we had a truss with a pinned connection right here and a rocker right here, we've got a member from A to B and a member from B to C, and one from A to C. Then we've got, it's 2 meters here, got a 500 Newton force, and we've got 45 degrees. Oops. It's a 45-degree angle. Okay, so in the method of joints, what we do is we look at each joint individually to solve for the forces in each of the members. Okay, so what we would do is we'd start with joint B because we already have a known force there. So if we look at joint B, and so the theory behind the method of joints is that this entire thing is in equilibrium. So if you look at just one joint, it is completely in equilibrium as well. So you treat it as a body and of itself, basically. So we've got our 500 Newton force here, and then we would have a force in this direction, and we'd have a force here. So we know that the force for B to C would have to counteract this 500 newtons, so it would act like that. So that's FBC. It's a two-force member, so it's acting along its line. And then for FBA, it would need to counteract the up of FBC such that it would be acting down like this. So what that was considered method 1, where by inspection you determine which members are in tension and which are in compression. Okay, and so the next method, method 2, we'd have our X and Y, we'd have our 500 newtons, but instead of by inspection figuring out whether or not FBC is going to act this way or that way, you just put all members in tension. So we'd put FBC in tension and FBA in tension. Okay, and then if you find that FBC is negative, like we will find because we know that it actually looks like this, you just know that FBC is actually in compression. So let me show why that, well, okay, first, so this is method 2. Assume every member in tension, then negative values are in compression. So basically, when we're looking at a joint, we have to expand this truss out. So it says FBA is acting there, but then we would have the free body diagram of our FBA, and we need to counteract this such that we would have FBA acting in tension. So when you kind of look at this, it almost looks counterintuitive, because if this is pushing down, it seems like it's pushing down on the member such that the member would be in compression, but it's not, because the member itself is going to, when you expand this out to the free body diagram, then these two have to counteract each other, right? So they're equal and opposite. So it looks like it's acting down, but in reality, this is a tensile force on the member. So you can see up here, if we then drew FBC, FBC would have would need an arrow acting in this way, which would put the member in compression. So, like, let's put it out here. So if this is FBC, and we're going to put it right there, then to counteract this force, we need FBC right here, and then equal opposite, because it's a two-force member, such that this one is going to be in compression. So when you're looking just at the joint, it's opposite of what you would think, because FBC looks like it's pulling the member such that it would be in tension, but because it's equal opposite, it's actually in compression. So be careful of that one, because I feel like it's counterintuitive, but just remember that this is just one part of the free body diagram, and if you expand the whole thing out, then each of these members has its own free body diagram where it's equal and opposite. Okay, so the procedure for this. So first, we're going to draw the free body diagram of a joint having at least one known force. That's why we started with B last time when we were looking at that example. And at most two unknown forces, right? Because we've got two equations to work with to find the unknown forces. The sum of the forces in the x and the sum of the forces in the y, such that we can only have two unknowns. Okay, next, when you're drawing the free body diagram, you're going to use either method 1 or 2 to determine the direction of the unknown forces Okay, then you're going to orient the x and y axes such that the forces can be resolved into their x and y components So you're going to use the sum of the forces, the x is equal to 0, and the sum of the forces in the y is equal to 0 to solve for the unknown forces. And then we use the calculated results from that joint to calculate the other joints. So the next joint chosen should not have more than two unknowns. Because just like all the other joints, we've got the sum of the forces in the x and the sum of the forces in the y. So we can only have two equations, two unknowns. And that's it.